The Open University of Hong Kong recently hosted an Earth Day Summit. Political leaders, academics, and representatives of green groups and industries gathered to address a range of environmental challenges. In the following session, two green industry leaders presented practical solutions that can help solve difficult problems. First, engineer Chris Chong, Managing Director of Hong Kong District Cooling Company, explains how cooling buildings from a centralized source can save money and help reduce energy use and pollution.
First of all, thank you, the organizer, for inviting me to speak on this project, district cooling. For me, I've experience in district cooling for more than 10 years. I've been doing district cooling in other places, Hong Kong, China, and also Macau. It's my pleasure to share my experience here with you. The topic for today is coming 5. I will talk about the global trend, about what is happening, and then explain a bit what is DCS and why we need DCS and what is the benefit. And then I will use some example to illustrate the benefit of using district cooling. At the end of it, I will do some kind of concluding remarks. So if you take a look at this chart, if you take a look at 1970, in this chart, the darker the color, the more the urbanization. The red dot in the chart is about megacity, more than 10,000 people in the city. So you can see the global trend of urbanizations that's happening from 1970 to now, and also it will continue. And there will be more big cities in the world. As you can see here, there's a lot of red dots. There's the studies in 2050, 70% of the world populations will be in cities. And that means they will use a lot of resources, there will be environmental impact and social challenge. As you can see, a lot of consumption will be in future consumed in cities. For example, 7% of the energy of the world will be consumed in cities. That means there will be a lot of greenhouse gases, and also global warming will be as a result of the urbanization. I think the key for us is not to stop using energy, and how to use energy efficiently and how to produce efficiently, I think is the key for us to survive. So from our company point of view, if you want green economy, you need innovation, or it will not happen. If you use our existing way to do the same things in future, it may work, but I don't think it's efficient. So if we want to do things, we need to do things differently. How to do it in an innovation way, this is the way to go. This is my company opinion and also my personal belief. So, half full or half empty? So why do I bring this to your attention is because you will see urbanization will be a risk. There will be a lot of people crowding in the city. But if you take a look at the positive side, if we can well manage the city, it can offer economic scales. We can do things differently, you can do it efficiently when comparing with remote area. So for us, that's an opportunity, it's not a risk. So what is district cooling? It is in fact a centralized cooling plant, and then there will be some pipeworks deliver the chill water to different buildings, and in each individual building, there is a intake room, or you call it substations. So the concept is no different from power. If you consider the district cooling plant as a power plant, the pipework is an electrical cable, and this intake room as a transformer. It's the same. So we are basically transforming or transporting energy from one centralized plant to the individual users. So according to EMS studies, district cooling is more efficient than freshwater cool and also air-cooled chillers. And I'm going to explain to you why there's a saving because of centralization. The first simple reason is economic scales. Big machine is more efficient than small machines. And this is the reason why you don't do your generator at home. You need a power plant. This is one of the major reasons. And if you have putting small load together, then you can operate the machine in an optimal way. If you only have one machine and one customer, you cannot manipulate the machines. But if you have more customer connected, then you can operate your machine in different loading, make sure it is at the optimal design capacity. Another environmental benefit is this is individual plant. For example, if you have one building, normally you have 2 units and 1 standby. You have 50% spare capacity. If you have another building, etc., etc., that means the cumulative spare capacity is 50%. But if you have a centralized district cooling plant, I also need one standby, but that is 25%. By doing this, you can install less chillers. That means less refrigerants. That also help the environment. The other reason why there's a saving from reduction in installation of the district cooling is if you have a building A and building B, they have the same pattern of usage. If you group it together, it will become A plus B. But if you have a building A and building C, if you put them together in a systems, the cumulative loading will be A plus C. You can see the installed capacity can be less. This is diversity. This is a common practice used in electricity. That means in the extreme case, there is say a nightclub versus an office. I can put one machine to serve both of them instead of two machines. This is an easy example to illustrate this idea. The other way is district cooling. If you use this, just like electricity, if you want more loading or less loading, you just add more plate. It's more flexible. If you want more cooling or less cooling, we can just adding more heat exchanger plates, then you can give more cooling to the customers. That is more flexible. If you don't use district cooling, you will see you need to build your own chiller plant room. You need to build your own cooling towers. You need to build your own water tank. And there's something you cannot see is the electricity. 50% of the electricity in the building is used for air conditioning. You need to use the transformer house and also the switchgear room, which you cannot see here. But if district cooling, we only need a heat exchanger room. And the area created, you don't need any more the cooling towers. You do not need the water tank. That you can use for other commercial use, or you can use green roof or whatever you like. And also, you can save some area. The building can be designed in different shapes if you want. This is the heat exchanger room for a 30-story building. In the past, you need a chillers, you need water tank, and now you only need a small substation like this, and it can serve a 30-story buildings. Without DCS, you need to have your cooling towers that is hosted normally in the rooftop of different buildings. But if you have district coolings, then it can be centralized and controlled in a controlled way. By doing this, it can reduce the heat island effect for the cities. As you can see, this is the case in Hong Kong. By reducing the heat island effect, it can reduce the cooling consumption in building. That bring also a good effect to the whole environment. And also, more centralized plant, you need less people. And people can be used to focus on optimizations, how to do it better. The coming slide, I think, for me, is very interesting. Why the choice of technology? What do I mean? If you use a typical energy systems like this, I will bring you through this. Look complicated, but in fact, it is very simple. You need generation, and you need grid, like electricity network or district cooling network or heating network. And then you need users, just like transportation, building, and industry. And when you produce this, you can have storage. So I will explain why I bring this chart to you. I think this is an important concept of centralization. If you have only a small building, you cannot do this. But if you have a centralized grid, you can do this. In relation to the cooling, for example, in your building, when you have the network, you can use different technologies like gas absorption chillers. You can use waste heat for the absorption chillers. You can use thermal energy storage. And you can use cogeneration, which can increase the efficiency of the overall systems. And all this technology, you cannot do it if you have a small building. If you have the scale, you can employ all these technologies. What are the DCS worldwide? So Veolia has a lot of district cooling. We are the largest district cooling company in the world, and also in the US. There's a lot of different cases already done for the district cooling. And the first one here is 1970s in Paris. There is district cooling already. So it is not new technology. It has been there for 40, 50 years. So the project I work on is the Kai-Tak is the first public district cooling in Hong Kong. When this is fully built, it's 80,000 RT. What is the concept of that? A grade A building requires 30,000. Now it's 80,000. That means about 30 buildings, 30 grade A buildings we can supply. And from the government studies, you can see we will have a different type of user: cruise terminal, hotel, hospitals, government building, commercial malls. When fully done, it will be save about 85 million kilowatt of electricity, based on the reason that I explained before. The project has been completed in phases. We have 2 plans, one north and one south. Some of the user has already been using us, like the cruise terminal and also the TI tower. One characteristic of this project is you use seawater. Seawater has a lower temperature. If the condensing temperature is lower, the efficiency of the system is higher. And this is one of the good reasons that this government wants to use district cooling using seawater. And this technology is difficult to use if you have individual buildings. Let's take a look at other places like Singapore, Guangzhou, or Middle East. You can see there is big ice storage inside, and this is a cool, chilled water tank. This is some kind of ice for the ice storage, and you can use other medium as well. In this project, they use ice or cold water. And why they do this? This is quite controversial, but I will bring you through this. This axis is about the hours, and this is the percentage of the loading of electricity. I'm from power industry. When I was young, normally they use the nuclear or the hydro as a base load. When they have more electricity consumption, they will put less efficient machines to serve the peak. For example, diesel. For example, the combustion turbine. The efficiency is lower, the cost is higher. So if for cooling in a typical building, this is also the hours. Normally we turn on it during the afternoon hours or the office hours. If we can find a way to move the cooling peak to this nighttime, I think this is the reason for using ice storage. And why we do this in China, for example. In China, the tariff between the nighttime and the daytime is 1/3, only 30% at night. I think the government also gives incentive for the industry to move their afternoon peak to the nighttime. This is one effective way because cooling is a big user during the office hours. And by doing this, they can less dependence on the less efficient generation machines. And also, in some cases, because you got the storage of cooling, in case there's no electricity, you can still have some cooling because you have ice. That is very important concept. Is if you look at the city's perspective, it can reduce or defer the power infrastructure development. There's another interesting project we have in Barcelona. This is a district heating and cooling plant. For the heating, they use wood chip. For the producing of the heating for the customers during the winter time, that's very interesting is they use the cooling from the LNG terminal. You know LNG, it is minus 165 degrees. When they degas it, there will be a lot of free cooling. And in this project, we use the free cooling from the LNG. If we don't use it, it will dump in the sea anyway. So we use this to power our own district cooling network. And there's another interesting project we have in Kuala Lumpur. It's a gas project. It uses gas turbine. It drives the electricity to drive the electricity chiller. And they use the waste steam for the driving chiller as well. They use a steam-driven central. They don't use motor. They use the waste steam to drive the centrifugal chillers. And if you know electricity well, gas turbine, we need a stable load. That means at night time, when the consumption is not high, we use the electricity to produce ice. That makes the system more efficient. This is my favorite project. Unfortunately, it's not done by us. It is using deep lake water cooling. In Canada, the lake water is very cold. It can be down as 5 degrees C. They just pump the cold river water using some kind of filter, and they have heat exchangers, and they transfer the cooling, the 5-degree cooling, and then it used to power the district cooling system. The interesting point is, I would like to highlight to you is, after this process, the water is pumped into the city water. So it's not waste. You pump the water anyway and take the cool and power the whole city. I think this is a very good idea. The other project is I just mentioned is 1970s. It has been built for a long time, so it's very proven district cooling in the world. After saying all this good thing about district cooling, I need to caution a bit is when we build district cooling, we need to think about the tunnel, the planning of the pipeworks. That need to be done. That need to be careful. And apart from that, demand uncertainty, we need to think, because we are an infrastructure company. If we build it, no user, we will lose a lot of money. We need to make sure economically it makes sense. Otherwise, it will scare off the investor. So, as a conclusion, after I say all this about the district energy, district cooling, this idea is confirmed in the United Nations Environmental Program. You can see they issued a book called District Energy in the City, Unlocking the Potential of Energy Efficiency and Renewable. And you can see here, is a district energy system is the best practice approach for providing a local, affordable, and low-carbon energy supply. District energy represents a significant opportunity for city to move towards climate resilient, resource efficient, and low-carbon pathway. And it's basically what I explained before. I think it's a good concluding remark for my talk here. And last but not least, I want to say again, the green economy will be an economy of innovation. We need your help to reduce the carbon footprint. So this is the end of my presentation. Thank you.
In the second presentation, Professor Engineer Steven Wong, Managing Director of BillionGroup Technologies, recounts some of his experiences with improving industrial design in ways that cut energy usage by startling amounts.
First of all, thank you very much for the invitation by Professor Casey Ho and the organizer to me, such that I have the opportunities to share my humble experience in energy efficiency improvement and also some waste to energy experience in the last 2 decades in Hong Kong, China, Asia, and also in Germany and also in Europe. I would focus on 2 things, energy efficiency and also waste to energy. Before I start my sharing of my experience, let me ask you one question. When we always talk about carbon emission, we always compare the current carbon emission or greenhouse gas emission comparing to the post-industrialization. Am I correct? Why? Why we always compare the carbon emission to the post-industrialization? The answer is, we always think that we have the answer behind this question because we think all the carbon emission is coming from industrialization. Am I correct? Yeah. Then I ask one question down. Why industrialization will cause so much carbon emission? We know the answer. Carbon emission is caused by industrialization. But why industrialization will cause so much carbon emission? The answer is low energy efficiency. I'm not talking about theory. I'm talking about my actual experience in the last 2-3 decades. And I've been working, helping a lot of industry, various from injection molding, electroplating, metal stamping, cement, asphalt, electronics, toys, dyeing, whatever you name it. I've been working in the last 2 decades for various industries in Hong Kong, China, and in Asia regions. Out of this analysis, we found that most of the manufacturing facilities' efficiency are extremely low. If you ask me a question, hey, Steve, what is your summary of those industries when they have employed your expertise to improve the energy efficiency, then what energy saving could be achieved? How much energy could be achieved? From my last 20 years experience, after my assistance for the manufacturing process, on average, the energy consumption could be reduced by 50% or even higher. I will share some of my experience in what specific area that most of the industry have been wasting the energy. In electrical power losses, in mechanical ventilation, an air conditioning system, in lighting solution, mainly in manufacturing system. Particularly in China, I think most of the energy are being consumed in manufacturing industry. Boiler system, thermal insulation system, wastewater treatment, and renewable energy. Say, for example, I'll give you some information. Hydropower is a green energy, right? If total hydropower is 1 unit, do you know how many units available for the solar power? Renewable energy. We have wind energy, biogas, whatever. The most available renewable energy among all is solar. Comparing the magnitude, 1 unit is from hydropower, hydro-water power, and how many units from the solar? Anybody knows about that? The answer is 2,850. according to the global survey. Therefore, the most abundant and also available renewable energy in the earth is solar energy. This is why we should make use of the solar energy. Maybe I can highlight some of my experience, that the shortcomings coming from the industry in the last 2 decades. On the electrical system, a lot of factories are over-providing the supply capacity in their factory. On a financial term, of course, they have spent too much money, because when you install a transformer in your factory, no matter whether you use it or not, when you install the transformer around 1,000 kVA, you have to pay 24,000 RMB per month. That means that almost 300,000 every year. Therefore, I've been seeing that in a lot of factories, they have over-providing the power capacity in their sites. That's number one. The second thing is that even though you idle this power supply in the factory, they are consuming energy, even though you do not use it, because it will consume hysteresis loss in the core of the transformer. That will consume energy. This is why we always advise our client not to overbuild the power supply system in your factory. Particularly, I think in the years coming, when we apply the energy efficiency improvement in various energy systems, the overall energy consumption will come down drastically. Then for electrical system, a lot of loss has been consumed in the distribution power, in the distribution. I have a factory asked me to be their consultant, helping them in Dongguan. In one single year, we help them to save energy in terms of money around 30 million. You could think of how much energy they have wasted. And then one of the significant waste is in the power distribution. Not outside the factory, inside the factory. Because they only install the capacitor in the main board. But because once you install the capacitor in the main board, it is good for power distribution, but only from the perspective of the supply company. There will be no good internally. Therefore, once the client adopt my advice to install the power factor correction in the load center, therefore they could immediately save a lot of energy running from the main board to the load center. And then, in most of the industry, they installed mechanical ventilation. In most of the mind of the factory owner, ventilation fan, just small power, just let it run. But in reality, in some factory, some workshop, I found that the energy consumed in ventilation system is even higher than the manufacturing processes. That's the fact. Therefore, after refining the design of the ventilation, a lot of energy consumption has been saved. On the left-hand side, this picture is one very famous factory. It's in Bangladesh. I have a lot of factories in Bangladesh. Before my helping, I found that they are running a lot of ventilation fan. But do you think there is a problem in this ventilation system? Or this system is good? What's the reason? Short circuit. This factory owner is quite generous in using money and energy in running ventilation fan. But once the window is open, actually all the air will coming up from the window directly to the outside. There will be no effect in cooling down the indoor temperature, right? And also extracting the indoor waste property. Therefore, after a good design, all the system has been improved, and the energy consumption has been drastically reduced. 50% is not an extravagant figure. In China or in Asia, a lot of this kind of evaporative cooler has been used. But nowadays, I highly recommend the factory to switch from this to this kind of helicopter fan, because one of these evaporative cooler, they will consume around 1 to 2 kilowatt power consumption. But the area serving is quite limited, only I think around 1,000 square foot or less. But this kind of helicopter fan, this can serve up to 1,000 square meters. The power consumption at the optimum running condition is only consumed 1.5 kilowatts. We actually measure the consumption. Therefore, we can drastically reduce the power consumption in ventilation over 50%. And in air conditioning, from my humble experience, most of the saving in air conditioning is not in air conditioning itself, but in the building envelope. Say, for example, for a building having a cooling ton of around 100 air refrigerant tonnage, 100%, you guess how many percent is for catering the internal people, and how many percent catering for the external heat gain? Maybe I ask this question in a way. The majority is for cooling down the internal heat gain answer, or to cooling down the external heat gain coming into the building. External, raise up the hand. Exactly right. I can share with you that sometime up to 80% of the refrigerant loading is running to cool down the heat gain from the outside. I had a small job in New Territory. After having this kind of improvement in thermal treatment for the building envelope, for air conditioning systems, we can switch down 3. Only 1 unit running. We save 3 units. Then you can imagine how much energy has been wasted before the retrofit. Therefore, starting from now, in order to increase the energy efficiency, in order to maximize the usage of our energy, make sure that we have to bear in mind looking about building envelope of our premises. Try to eliminate or avoid any energy wastage in cooling down the external loading. And in some manufacturing system, a lot of bad design is that, the indoor temperature is very hot. Therefore, the owner of the factory is good. They're passionate with the workers there. Therefore, they add a lot of ventilation fan here and there, here and there. Say, for example, the heat source is right here, and then we install a lot of fan in the perimeter of the building such that they can expel the heat out to the outdoor atmosphere. Is this a good exercise? No. One thing is that, the heat source is right here. And then if we install a fan over there, then we are trying to move the heat spread around the whole factory, right? That's point number 1. The second point is that normally during the manufacturing processes, apart from heat, what you will produce? Pollutants, VOC, am I correct? If you install such a system at that location, then you're trying to push the pollutants from here all around the factory. And then all the workers inside the factory are being polluted with the dangerous of the pollutants, dangerous material. Therefore, it is not a good design. The best design is that when you create the pollution at the source, then you have to remove the pollution right at the source. Am I correct? This is the right solution. Therefore, after using this kind of approach to the factory, we have a lot of factories to improve the indoor air quality and also save a lot of energy by reducing, shutting down all these perimeter ventilation fans. Lighting system normally constitute around 10% of the total consumption in a factory. In North America and United States, also in Europe, in the past 5-6 years' time, our team has been helping a lot of big factories to reduce energy consumption in lighting system, including Coca-Cola, Pepsi, Kellogg, things like that. After using the latest advanced lighting system, you guess how much energy we can save in lighting system? 10%? 50%? 90%? 95% maximum. On average, 90%. Therefore, I think we have to look upon whether are we wasting energy in the lighting system. Apart from light source, we're talking about T8 to T5, T5 to LED. There's only one spectrum, one element in the energy saving in lighting system, talking about the light source. But in reality, a lot of simple things can be used to reduce energy consumption in lighting. Say, for example, in this factory, the lighting is at the ceiling of the plant room, right? But where is the task location, where the task is being carried out? Down on the floor, am I correct? If you put the lighting on the top floor, you will waste a lot, even though the lux level there will be 1,000, but down to the floor is only 50. Therefore, you're wasting a lot of energy in illuminating the lawn task area. Back to this picture, all the lighting was in the ceiling. But after my redesign of the system, they put all the lighting just on top of the sewing machine. By doing so, you could save more than 50% of the energy. For manufacturing system, a lot of example, we've been doing a lot. For sewing machines, I think you see these sewing machines when you and I were young. These sewing machines are still being used in some countries, particularly in the developing countries. But after improvement of the sewing machine's efficiency, we could also save 60% in energy for the sewing machine. Then after applying energy efficiency, the overall saving could be over 50%. Then talking about switch to waste. This chart will show that our experience in Germany after adopting properly waste treatment the total CO2 emission, carbon emission can be actually reduced. In China, totally around 660 cities at the moment. How many cities are being surrounded by garbage and municipal solid waste? Do you know the number? Do you know? 100? The answer is 440. 440 cities being surrounded by garbage, municipal solid waste. And then this waste has generated a lot of pollution in air and also in water, and also deteriorating the health of the people. Therefore, we have an imminent need to try to solve this waste problem in China. And also, this problem is not only unique in China, but also in most of the developing countries in Asia. I will introduce a concept because in China, they do have waste-to-energy plant. But the problem is that they directly fire the waste into steam. Bear in mind, most of the waste in China, the water content is very high. Do you know how high it is? In monsoon season, up to 80% moisture content. In normal, also 70%. If you fire this waste in the incineration plant, you're actually firing water. And then the energy efficiency is very low. And also, once you fire this waste, the temperature of the burner will be around below 1,000 degrees Celsius. If that's happened, then one significant drawback is the generation of dioxin. Therefore, I think in Germany, starting from 2005, EU and Germany has to follow the EU legislation that no untreated waste can be dumped into landfill sites. Since 2005, no untreated waste could be dumped into landfill sites. That means that all waste must be treated well before to landfill site. Running a waste-to-energy plant is quite difficult, not like running a coal plant, because for coal, you have a constant C value, calorific value. It's constant at around 25 megajoule per kg. But for waste incineration plant, the value is not constant, but also in different timeline in a year, like Chinese New Year, Easter holiday, or summer or winter time, the composition of the waste are different. Therefore, the internal C value of the waste are different. How you build a waste incineration plant to cater for different C value is extremely difficult. And also the efficiency will be very low. One more important point is that in designing a waste-to-energy plant, are you running it for 1 year, 2 years, or 3 years? Of course not. It must be running for the coming 25 or even longer. Am I correct? But in that case, bear in mind the demographics of a city. The economic situation of a city will change. That means the economic will change the city's behavior. In that case, the composition of the waste of a city will also change. In that case, the C value will continue changing. How do you design a plant to cater for all these changes? Therefore, if you strictly have to go design a plant just mainly for the waste of energy, then the plant will come out with very low efficiency. That's what we have seen in China right now. And then, how to tackle this problem is that we can apply a treatment called MBT to change this waste into a green fuel called RDF, refuse-derived fuel, in such a way that this RDF, refuse-derived fuel, can have a very high heat value, C value, up to 12 mJ per kg. That's proven. And then this RDF also can have a lot of applications. Can be used in power plant, RDF power plant, and also can use with Veolia regarding the DSC. Because once we have the RDF, we can send it to the DSC plant and then convert into heat. And then this heat can use to drive the district cooling. Therefore, we can use the waste to generate cooling for the whole area, rather than using the fossil fuel. In Germany, we always build the RDF plant next to the paper mill or industry. Therefore, we can directly use the heat generator to feed the industrial process. Then you can save a lot of energy. These are the CO2 emission reduction through using RDF. You can compare this brown coal, hard coal, oil, natural gas, and RDF. You can see that the CO2 emission, the lowest, is from RDF. This is a chart I wanted to highlight that. This is the year 2005. And then after 2005, you could see the numbers of RDF fire power plants in Germany has been sharply increased. The reason behind is that without the policy of the government, of the EU, there will be no such consequence. In order to move to a greener life and also to help our environment, we need our government to legislate some policy in order to reinforce more greener energy like RDF. Thank you very much.